Welcome! Today, we're going to tackle a fascinating problem. Our goal is to find all integer solutions x and y that satisfy the equation x cubed minus y cubed equals 61. This problem requires a mix of algebra and number theory, and we'll walk through it step by step. By the end of this video, you'll be able to use algebraic identities and the properties of integers to solve Diophantine equations of this form. Let's begin by observing our equation. We have x cubed minus y cubed equals 61. The left side is a difference of two cubes. Recall the algebraic identity for this. The difference of cubes formula states that a cubed minus b cubed equals the product of a minus b and a squared plus a b plus b squared. We can apply this directly to our equation by substituting x for a and y for bc. This gives us the equation. The product of xy and x squared plus x plus y squared equals 61. Take a moment to process what we've just done. We've transformed our cubic equation into a product of two factors. Now let's analyze our transformed equation. We have xy times x squared plus y squared equals 61. We are looking for integer solutions for x and y. This is crucial. When the product of two integers is 1, those two integers must be factors of 61. Let's find the factors of 1. 61 is a prime number. This means its only integer factors are 1 and itself. Since we're dealing with integers, we must also consider negative factors. So the complete list of factors for 1 is 1 to 1, -1, and -6y. This means our first factor, xy, and our second factor, x squared plus y squared, must be one of these pairs. This gives us 4 possible cases to investigate. We will call the first factor a and the second factor b. Let's repeat that for clarity. The fact that x and y are integers forces their difference and the quadratic term to be integers as well. And because 61 is prime, we have a limited number of possibilities for what these two factors can be. Let's begin by analyzing the second factor, b. We're looking at the expression x squared plus xy plus y squared. This term has some special properties. We can use a trick of completing the square to rewrite it. We can rewrite this expression as 1/4 of the quantity, 2x plus y squared plus 3y squared. Let's see why. If we expand the term, 2x plus y squared, we get 4x squared plus 4xy plus y squared. Adding 3y squared gives us 4x squared plus 4xi plus 4y squared. Multiplying by 1/4 returns us to the original expression x squared plus xy plus y squared. This new form is incredibly useful. Notice the two parts. First, 2x plus y squared. The square of any integer is always non-negative, meaning it's greater than or equal to 0. Similarly, 3y squared must also be non-negative. This is because 3 is positive and y squared is non-negative. This tells us that the sum of these two terms is also non-negative. Therefore, our second factor, x squared plus xy plus y squared, can never be negative. It must be greater than or equal to 0. Let's repeat that critical insight. By rewriting the expression through completing the square, we have proven that the factor b, which is x squared plus xy plus y squared, must always be non-negative. This single piece of information allows us to immediately rule out 2 of our 4 cases. Cases 3 and 4 required our second factor to be negative, which we now know is impossible. We have successfully narrowed down our search to just 2 cases. Let's start with the first one. Case 1, x minus y equals 1, and x squared plus xy plus y squared equals 61. From the first equation, we can express x in terms of y. Adding e to both sides gives us x equals y plus 1. Now we will substitute this expression for x into our second equation. Substituting y plus 1 for x, our equation becomes y plus 1 squared plus y plus 1 times y plus y squared equals 61. Let's carefully expand and simplify this expression. Expanding the terms, we get y squared plus 2y plus 1 plus y squared plus y squared, all equal to 61. Combining the like terms, we have 3 squared plus 3y plus 1 equals 61. This is a quadratic equation in y. Let's set it to 0. Subtracting 61 from both sides gives us 3 squared plus 3 minus 60 equals 0. We can simplify this by dividing the entire equation by 3. Dividing by 3 gives us y squared plus y minus 20 equals 0. This is a simple quadratic equation that we can solve by factoring. We need two numbers that multiply to -20 and add to 1. Those numbers are 5 and -4. So we can factor the equation as ey plus 5 times y sin 4 equals 0. This gives us two possible values for y, -5 and +4. Great, we have two integer solutions for y. Let's find the corresponding x values. Remember our relationship x equals y plus 1. If y is -5, then x is -5 plus 1, which is -4. This gives us our first solution pair. X equals -4, y equals -5. If y is 4, then x is 4 plus 1, which is 5. This gives us our second solution pair. X equals 5, y equals 4. We have successfully found two pairs of integers that solve our original equation from case 1. Let's quickly verify one of them. Let's check 5, 4. Is 5 cubed minus 4 cubed equal to 61? 125 minus 64 is indeed 1. It works. We're halfway there. Now for case 2. Case 2, x minus y equals 61, and x squared plus xy plus y squared equals 1. We'll follow the exact same procedure. First, express x in terms of y. From the first equation, we get x equals y plus 61. Now substitute this into the second equation. This gives us y plus 61 squared plus y plus 61 times y plus y squared equals 1. Let's expand and simplify this equation. Expanding the terms, we get y squared plus 122y plus 37221 plus y squared plus 61y plus y squared equals 1. Combining like terms, we get 3y squared plus 183 plus 33721 equals 1. Now let's form a standard quadratic equation by subtracting 1 from both sides. We have 3y squared plus 183 plus 3720 equals 0. As before, we can simplify by dividing by 3. This gives us the quadratic equation y squared plus 61y plus 1240 equals 0. Now, we need to solve this for y. We can use the quadratic formula. The quadratic formula is y equals -b, plus or minus the square root of b squared minus 4ac, all divided by 2a. For our equation, a is 1, b is 61, and c is 1240. Plugging these values in, we get y equals -1 plus or minus the square root of c1 squared minus 4 times 1 times 12i, all divided by 2. Let's calculate the discriminant, which is the part under the square root. 61 squared is 3721. 4 times 1240 is 4960. The discriminant is 3721 minus 4960, which is -1239. Here we have a problem. The discriminant is negative. The square root of a negative number is an imaginary number. Since we are looking for integer solutions, this means there are no real solutions for y in this case. Let's be clear on that point. Because we got a negative number inside the square root, the quadratic equation yields no real number solutions. As a result, there are certainly no integer solutions. Therefore, case 2 yields no solutions. We have successfully checked the second case and found no integer pairs. So, let's recap our journey. We started with the equation x cubed minus y cubed equals 61. We factored the left side using the difference of cubes formula. This allowed us to transform the problem from a cubic equation into a product of two integer factors that must equal 61. By completing the square on the second factor, we proved that it must be non-negative. This powerful insight eliminated half of our possible cases, leaving us with just 2. We analyzed the first case, x minus y equals 1, and found two pairs of integer solutions, 4 are 5 and 5, 4. Finally, we analyzed the second case, x minus y equals 1, and found that it led to a quadratic equation with no real solutions, and therefore no integer solutions. We can now state our final answer. The only integer solutions, axy to the equation x cubed minus y cubed equals 61, are the two pairs we found in case 1. These solutions are x equals -4, y equals -5, and x equals 5, y equals 4. To recap our learning goals, you should now be able to recognize a difference of cubes, apply its identity, and understand how to use number theory properties, like the non-negativity of certain expressions and the primality of numbers, to simplify and solve Diophantine equations involving cubes. Thank you for watching, and I hope you have found this explanation helpful.